Hello students, we're going to cover some more ideas as far as exponentials and logarithms go. We're going to explore looking at how to solve them by applying the properties. That's one of the most important applications when it comes to logarithms, is how to apply them to solving tricky exponential equations. So we're really coming to the apex of all the properties that we've learned and all the definitions for logs. One of the biggest applications is how to apply those to solving certain types of exponential equations. So we're going to look at solving exponential and logarithmic equations all in general. So depending upon what you have, there's certain approaches you're going to follow. So if you keep this main idea in mind, it will help throughout all the problem solving as far as equations go. So the main idea, and what we've been working up towards, is if you cannot solve something in exponential form, you go to log form. If you cannot solve something in log form, you go to exponential form. So the main idea is if you cannot solve in, and I'm going to say EXP for short, exponential form, then you convert to log. Then you convert to log form to solve, and vice versa. Meaning you go from log to exponential form if you can't solve in a log form. So as long as you hold that main idea in your mind when you're approaching a variety of problems to solve, that should get you through. So, and again, what we do is you apply your properties when you need to. So what you have to do is be very careful with your rules for logarithms and how you use them. Okay, so let's start with solving exponentials. Solving exponential equations. This is when the variable is in the exponent. That's how we defined an exponential function. So when we have a variable in the exponent, it becomes exponential. An equation, we have the equal sign. So there's two main ways. Okay. Solve, number one, solve by getting the bases the same. And setting the exponents equal. Okay, that's when you could get the bases the same. If you can, right? If you could get the bases the same, you set the exponents equal and then solve for x, or whatever the variable is. Number two, the other main way is if you can't get the bases the same, then you convert to, if you can't get the bases the same, you convert to log form and solve. Which you could do even if you can't get the bases the same, but usually it's a little easier to work with getting the bases the same. It really depends on the problem. So if you can't get the bases the same, then you go to log form. And here you stay with exponential form. So we're going to look at these two main methods. Let's start with some ones where we can get the bases the same. So here is two main ways, or cases sometimes I refer to that. Okay, here's some examples. Whoa. And in all these examples, when we're looking at equations, the directions are really to solve. So it gives you that flexibility to use any method you want, but of course, some methods just don't work sometimes, okay? So let's start with number one. Let's look at a standard exponential. And you might be able to do this one without writing anything down. You might be able to think this through and figure out what the value of x needs to be. But what we're going to do here is look at something that's familiar to us, and we're going to just work out the steps so that we have a guideline to approach every single problem with. So they just get sort of trickier as we progress. So here we have 2 to the x minus 1 equals 2 to the third power. So what I did here is I first want to backtrack, ask myself the question first, can you get the bases the same? And the answer is yes. Okay, then do. So what I'm going to do is, as I've showed, as a preview, say 2 to the x minus 1 is the same as 2 to the third power. Okay? Because 8 is expressed as the third power. And once my bases are the same, then I can set my exponents equal. So I'm going to set bases the same, which leaves me with the logic that these must be equivalent, the exponents. So this means that x minus 1 must equal 3. And of course, I just go ahead and solve. And then of course, fourth, check. For exponentials, as long as you did your work correctly, it should check out okay. For logarithms, you have to check because you have domain restrictions. So we'll get to that coming up. So my final answer is just x equals 4, and that makes sense. If we put a 4 in here, 4 minus 1 is 3, quick check, works out. Okay, let's do another. Looking for some good varieties here. If I had let's say I had e to the 2 minus x equals 1 over e. Just be where my e sometimes don't look e-ish, but that's an e. So can I get the bases the same? Yes, I can. I see that I have a base e on each side. So e again is about 2.7 approximately. So e to the 2 minus x equals e to the negative 1. Okay, because this is e to the first power in the denominator. I move it up, becomes a negative. Now my next step is, if I have the bases the same, then I equate the exponents. And I get 2 plus 1 equals x, or x equals 3. That's my final answer. Okay, there you go. Now let's go into the case where you don't have that ability to get the bases the same. So, number 3, I'm leaving that up on the board for a second. We're going to do a little variation. Now what we want to do is we want to solve 2 to the x minus 1 instead of 8 equals to 7. So you could see the challenge here. The challenge is that we have a 7 to use, and I don't think I have brought my calculator. There is one here. Okay, so what I'm going to do now is look at this and say bases cannot be made the same. So that's my first step. Okay. Bases cannot be made the same. There's no way I can make 7 in terms of base 2. So my go-to is, next step is convert to logs. Change to log form. Okay, let's change this to a logarithm. Now we have to remember the format, base over back. We start with our base. So I'm going to write this in log form. So it was so important to get fluent in converting to log form. We say log base 2 of 7, so base over back equals x minus 1. So there's my same expression in log form. Now, what I have to recognize is that this is some number value. And I want to know what that number is. It's some decimal number just below, we knew that log base 2 of 8 is 3. So it's just below 3. This is, I'm going to compute this in my calculator. My number is going to equal x minus 1 here. What is that number going to equal? Well, first I have to look at how I convert this to base 10. So I use my change of base formula to say log of 7 over log of 2. These are both in base 10 equal x minus 1. And basically, my value of x will be the number, x will equal 1 plus whatever log base 10 of 7 divided by log base 10 of 2 is. So this decimal number. Now that is an exact answer, so that's perfectly acceptable to leave it like that. However, if you want to approximate, you'd say this is 1 plus, and let's see what we have here. I'm going to say log of 7 divided by log of 2, and I get 2.8, just as we predicted it was close to the value of 3. So my x value is approximately 3.8, and that would be my final answer. Okay, so I changed to log form, and the third thing I did was solve for the x. Okay. So when I changed it to log form, that's what I got. Okay, and then I slowly solve for x, and you might have to approximate. If you need to. And then fourth, we do need to do a check. Now a quick check is just to make sure it doesn't give us anything that's restrictive. So this is not a log, so we don't have to worry about having a negative or a 0 in the argument. But about 3.8 minus 1 is about 2.8, so 2 to the 2.8 should approximately give me 7, and it does, and it works out. Okay, so that's what happens to those exponentials that you can't make the bases the same. Let's try one more with e. So number 4 here. Let's go ahead and solve this problem, which is 2 to e to the 2 minus x equals 9. Okay, so I noticed that I can't make the bases the same. Okay, there's no way I can express 9 in terms of e nicely. So I'm going to go ahead and rewrite it in log form. In this case, it's natural log form in ln form. Since we have a base e, this becomes ln base e of 9 equals 2 minus x. Now the question is, what is this number equal to? This is equal to some number. And then I would subtract 2 and multiply by a negative to get what the x is. So if I rewrite this, I'm going to switch places with this number and this x. So I'm going to have x x come on this side and this come on this side, x will equal 2 minus whatever the ln of 9 is. So remember, I could drop the e because it's understood to be an e base right here. So this is approximately, so this is my exact answer, but this is approximately 2 minus, let's see what ln of 9 is. 2.2. So my x value is approximately negative 0.2. And that's my final answer. Okay, that's how we do it in a nutshell. Now again, there can be very tricky problems out there, but the idea is to apply your rules and properties very carefully. Sometimes you'll have to do some manipulation ahead of time before you convert to log form. But that is the main idea. Okay, let's take a look at solving logarithms. Now these are going to have an extra twist due to their domain restrictions. Okay, so in the same way, we're going to have two main ways again, or cases. So the two main ways or two main cases are, number one, solve in the log form, if you can. Sometimes you can just keep it in log form and approximate it, okay? Number two is convert to exponential form to solve. Well, sometimes it's in log form and the x is buried inside the log, right? So when the x is buried inside a log right here and you have to solve for it, you're going to have to get it out. And the only way to get it out is by converting. Now, one thing that's very important with log equations, so what you want to remember is you must check log equation solutions since you have domain restrictions. Very important. Okay? You have to make sure that you don't have a negative or zero that's produced in the argument, i.e. So if you find, let's say, x equal to -1 and your equation is like log of x, okay, this is not possible. So we would cross out that solution, okay? So if you find that you solve for something and when you put it back in your log equation it produces a 0 or negative, you have to toss that solution out. So let's jump right into starting to solve some of these. Looking for a few good problems. All right, so what do I have here? If I have log base 2 of 16 minus x equals, let's say, 4, a case like this. What I would do in this situation is I would see that, sorry, I forgot to say examples, and we're going to solve. This is my first problem to solve. and I'm giving a logarithmic equation. Now, not everything in the equation is a log, so what I want to do is solve the logs and see, do I need to convert this? Well, in this case, this is just an equation where I have a log, but I can figure out what the log value is. So you could use your change of base formula, or you could think about how to evaluate this. So this is equivalently log 16 over log 2. So there's a number value, minus x equals 4. So if I were to solve for this, I could just go ahead and get my x by itself. So here, my first step that I see is I ask myself, can I solve this in log form? Yes. So I don't have to convert. There's no converting. So what I do is I just solve for x and check. Okay, so in this case, I already know what the solution to this is, and you could evaluate this in your calculator. I'll come up to a nice number because this is really 2 to what power gives you 16. This is the number 4 minus x equals 4. So we just end up with a linear equation here. And this becomes 4 plus 4 equals x, or x equals 8. That is your value. The next thing that's up is, let's say we had ln of 3 minus 1 equals 2x. Same thing goes here. Okay, we have logs, in this case a natural log, mixed in with our equation, but we could just leave it as is to solve because we could figure out the value. So this is really just ln of 3 minus 1 divided by 2 equals x. It's going to be whatever this value is. So if we look at what the ln of 3 is, we get 1.1. Okay, so we get 1.1 approximately minus 1 over 2. So we get about 0.1 divided by 2. And I should be able to do that. Approximately equal to x. So what we have is x is approximately 0.5. And that's your solution. And you can plug that in, and you can see that's a good approximation there. All right, so the next set, the other cases are, all right, when we get the x tangled inside. Okay. So number 3 is, let's solve something like this. The log of x equals 3. Now, how do you solve this? You would look at this and you'd say, well, my x is inside a log. The only way to get that out is by putting it into the exponential form. So I want to know what this value is, and this might be a little harder to see as far as understanding what it would be close to. It's always a good idea to try to approximate these. Now remember, there's an invisible 10 here, so this is base 10 of x equals 3. Okay, so what I'm really trying to find here is 10 to what power give me x. That might make it a little clearer on what that value would be. So what I'm going to do is, first, I'm going to see that I'm going to convert this to exponential form. Okay. And then second, I'm going to solve. So what I'm going to do is just go ahead and convert this to exponential form. So here's my log form. Exponential form is 10 to the 3rd power equals x. And lucky for me, my solution just comes right out quickly. So what I have is solve, and then I did that, and third, I check. Okay, that makes sense. If I put a 1,000 here, 10 to the third equals 1,000. And 1,000 is positive and not a negative, so perfectly valid. Okay, let's do ln. ln 1. If I have the ln of x minus 1, and what was equals 3. Okay, that's what I have written down. Okay, how do I solve this one? Well, here, again, it's a little harder to see because you have a base e. So I haven't personally met anyone that can do powers of e approximations in their mind, but in their head, but maybe you have. It's a little harder. I can get a ballpark figures. But here I can see that there's no way I could work with what I have to get the value of x. I would have to convert to an exponential form. So as an exponential, again, there's an understood e here. This becomes e to the third power equals x minus 1. And then this, you're solving for the x, which you're perfectly capable of doing now. You've untangled it. You've gotten it out of the inside of the log because right now it can't be touched or manipulated. Now this becomes, if I add 1 to both sides, I get x equals e to the third plus 1, and which means x is approximately going to be, if I compute my e value, I get about 20.1 plus 1, so x is approximately 21.1. Okay, and it falls all together. So now I just double check. Second, solve, check. At this point, I think we're good on our steps. So we'll be writing fewer and fewer. So 21.1, we make this a little more apparent. 21.1 minus 1 here, okay, gives you 20.1. So e to the third is about 20.1, and that is on target. Okay, let's do some mixed problems. Let's say I had, now there could be some very messy ones. Now we're just going to do a mix. Solve. And I'm just going to go ahead and jumble exponentials and logs together. A few more examples and you should be good to run with the exponentials and be able to solve a variety of them. Okay, I like this problem. 9 to the x minus 1 equals 1 over the square root of 3. Okay, this one might be more of a challenge. However, when I look at this, I'm thinking it's exponential. I can either solve it in exponential form or I can convert it to log form to solve it. So the key idea here is the fact that I'm recognizing common base. Looks like I can make the bases the same. So my thought process is base is the same. And the answer is yes. So I can work with the bases as is. So here, my base system I want to work with is 3. So I'm going to convert this 9 to 3 squared, which is all going to be put to the x minus 1 power. Okay, a few tricks involved here. Now this is a base 3 as well, so I'm going to take this one step at a time. This is 1 over 3 to the 1/2 power in the denominator, which I further want to simplify. Right now these bases are not the same. And my next step is 3 squared to the x minus 1 power is really 3 to the 2x minus 2 power, correct? So this now is in terms of base 3, and I've simplified my exponent, And here I bring this to the numerator and I get 3 to the negative 1/2. And now my exponents must be equal because my bases are the same. So now I have 2x minus 2 equals negative 1/2. And I get 2x equals 2 minus 1/2. And I divide by 2, and I get x equals, I'm solving for x. So at this point, after I make my exponents equal, I just solve for x. And what I have here, 2 minus 1/2, is really 3/2 over 2, which is 3/2 times 1/2, which is, so remember, dividing by 2 is the same as multiplying by 1/2. I get 3/4. And that is my final answer. Okay? So it looks like a little bit of mess, but the idea is first to recognize base 3 and slowly convert this whole side to base 3, a simple base 3 unit, and convert this whole side to a simple base 3 unit. And then it's just, doing a lot of the little tedious algebra steps after that. So if I check, I should get that. And it does work out that way. Okay. So 2, let's look for another problem. Maybe not so evident. Let's see here. Number 2, if we had this, we obviously can't make the bases the same. So, no. So then we got to set exponents. No, we can't. We go to convert to log. Okay, that's our first thought process for this problem. So this becomes log base 4 of 7 equals x plus 2. Now this is doable. Now my solution for x will be, I'm going to subtract 2 from both sides. So this becomes x equals log base 4 of 7 minus 2. So I'm going to look up what this approximate value is, which is log of 7 over log 4. Plus 2. And that will be approximately, let's see, log 7 1.4. Okay, 1.4 plus 2 is about 3.4. And that is your final answer. Some other ones that come up, let's go ahead and do. Let's see. There are definitely quite a bit that come up. Let's do one more log, and then we'll call it a day. And do number 3. Let's do log base 6 of x plus 5 plus log base 6 of x equals 2. So now I have a log equation, and I want to think about my approaches for those. So what I do with log equations is I try to work with them if I can, but I'm already seeing that I have internal x's, and the only way to bring those out to solve for those is to convert to exponential form. Here, to convert to exponential form, I must use my properties. So what I want to do first here is rewrite as a single log to convert to exponential form. Okay? So, and what I've noted before this is no, can't solve in log form. I've already noted that I can't solve it in the format it's in. I have to change it to exponential form. So going back to our properties, recall that these, when we're adding these are both positive. So it's like multiplying the arguments on the inside. This becomes log base 6 of x times x plus 5 equal to 2. So now I've written as a single logarithm, apply my properties, and you can see concisely that this is the same equivalent as 6 to the second power equals x times x plus 5. And we can solve this. This becomes 36 x squared plus 5x. And we ended up with an equation that's a quadratic. So we've had a log equation that's transformed into a quadratic. So what we have is x squared plus 5x minus 36 equals 0. And if I go through this and try to solve it, I want to find the factors that multiply to minus 36 but add to positive 5. This becomes x and x. Here I can see a plus 9 and a minus 4. Let's see, plus 9x minus 4x, add up to the 5x in the middle, and multiply out to minus 36. So I found the combo. So now I have to, my equation is transformed from log to exponential, now a quadratic. So I have to apply all my knowledge of all the different techniques as I go along. Now to solve a quadratic by factoring, I set each factor to 0. And my potential solutions are x equals minus 9 and 4. I say potential because with logs, you must check. So here, I have to do a must check. Okay. So notice, if I do a check, and I'll do it over here, since it is our last problem, and we can, I like this. If I claim x equals minus 9 as a solution, I should be able to put it into the original. And see that it works. Now, I could go through all the details of knowing the values, but right here I would stop and say, well, wait a minute. A negative 9 will produce a negative here, right? So all I have to do is have one violation by having a negative in the argument, and the entire solution is tossed. So this is not possible. Okay. But the x equals 4, let's see what it does. If I substitute 4 in place of every x, I end up with 4 plus 5 of this log base 6 plus 4 for this one, and these are perfectly fine. And if I did the math, I would see it comes out and works out. Okay. So 4 is my only solution. So this is a long problem, and it took a lot of knowing a lot of different pieces. There's a lot of practice of a lot of skill involved, which is great. So this problem eventually gives me the solution of just x equals 4. So the idea is convert to, if you can't solve in an exponential form, convert to log. If you can't solve in a log form, convert to exponential. And the problems get trickier, but if you apply your properties correctly and your skill set correctly, you should eventually get the correct solution. Thank you, and we'll see you in the next series of lectures.